Okay, so yesterday we finished off by sort of proving that for the irregular graphs, lambda 2 and lambda n, well, the expansions of this graph. And we sort of left wondering how large again this lambda 2 and how small rather is lambda 2 and lambda n. We know that the larger one of them is at least gross proportionally to square root of d. But it would be interesting to know if we can get bounds for each individual one of them. So this was addressed early 1990s by Alon and Boppana, who proved that if G is the irregular graph, with diameter capital D, meaning there are two vertices distance capital D apart from each other, then lambda 2 has to be fairly large. So the main term is proportional to square root of d. And then we have the error term. So let's, before moving on to the proof, let's discuss a little bit what this theorem means. So first of all, sometimes this addresses all the regimes, regardless of whether d is constant or grows with n, as long as we keep this dependence on the diameter in the error term. But quite often you will see this stated as let d be a constant and n tends to infinity. Then lambda 2 is at least 2 times square root of d minus 1 minus little of n. Little of 1 in n. Which is obviously true, because if d is constant, then the number of if you fix a vertex v, then the number of vertices distance k apart is bounded about by d to the k from a given vertex. So when you sum them up, you'll see that the diameter grows at least logarithmically in n. You can get a bit more precise estimates if you want to, but basically that's the case. So this error term really tends to 0 as n tends to infinity. However, that's no. It gets much more tricky if d has any sort of growth dependence on n. So that's why I prefer this first formulation over this one, because that sort of addresses the case when d has some dependence on n a bit more precise. Okay, so now suppose we don't really care about this constant 2 in front, and we view this as lambda 2 is at least constant times root d. Then, as long as the diameter is at least 4, then this implies that our second largest eigenvalue grows at least like constant times root d. But if diameter is 3, this bound tells nothing. Because the floor of d over 2 is now 1. So the main terms cancel and we are left with a constant. That's not particularly helpful. And this can unfortunately happen when d is roughly n to the 1/3. So in general, if you only look at sort of the worst case scenario amongst the irregular graphs, this form of the Alon-Boppana bound sort of breaks down already at a quite sparse version. It's still good because it addresses a bunch of regular graphs where the already like in as a polynomial in n, but it's slightly disappointing that we don't get further than n to the 1/3. Some bound on.
Sorry, what's the meaning of the capital D?
So D is capital D is the diameter of the graph.
What diameter?
So diameter means the maximum of the distances of vertices.
Oh, thank you.
So basically, that's a good question. So if we have a d-regular graph and we fix vertex u, then the neighborhood of u has size d. The vertices which are at most distance 2 apart, they are at most d times d minus 1 of them, because everything over here has d neighbors. One of them has to be u. At most d minus 1 sort of gets further and further away from, and so on. On the next level, we have at most d times d minus 1 squared. So basically the point is, if d is constant, then we know that somewhere right here, there's a w, which has such a distance between u and v, u and w is roughly logarithmic. So we know that this diameter is going to be large. But that sort of also sketches a proof why this is a natural barrier, because when d is roughly n to the 1/3, the log d of n is roughly 3, where it breaks down. Yes.
We do have the condition that G is connected, right? Or we can just substitute D into infinity and just get the one.
That's a good question. We don't need connectivity because if it's disconnected, then the second largest eigenvalue is already D. That's because if the graph is disconnected, let's say V1 and V2, then if we take the indicator vector of V1, then it's a eigenvalue D. Indicator vector of V2 is a eigenvalue D, and these are orthogonal. So I'm trying to avoid the verse of interlacing because I try to use as minimal amount of linear algebra, but I think at some point I have to appeal to it. So by interlacing, if you don't know what it is, then maybe during the break it's good to have a look at it. We know that the second largest eigenvalue is at least D. Or actually, in this case, it's exactly D. Yes.
But does this mean that the second largest eigenvalue is always positive?
Yes, that also follows from interlacing as long as G is not the complete graph.
Yeah, but I think this did not exclude the case that G is complete.
If it's complete, the diameter is.
Well, technically, I think for complete graph, the diameter is 1. So this then goes to minus infinity. So -1, which is the second largest eigenvalue, is greater than minus infinity. So I think I'm good. But yes, you should really think this as the graph being fairly sort of sparse, which guarantees that lambda 2 is non-zero and in fact positive, because complete multipartite graphs are the only ones where lambda 2 is 0. That brings me to naturally to the third remark, which is some condition on D is needed. As lambda2 of Turan graphs is 0. So for example, lambda2 of the complete bipartite 0. That being said, there's quite a big gap between them. So n over 2 is noticeably larger than n to the 1/3. So yes, we can't get all the way up to half n, but maybe there would be a way to push it beyond n to the 1/3. And tomorrow or Thursday, probably on Thursday, we'll actually see what happens in this gap. And last year, it was basically proved that among D regular graphs, either G is close to a Turan graph or lambda2 is large. So basically, now there is a very strong form of generalization of Alon Boppana theorem, which basically characterizes lower bound for lambda2 apart from trivial instances. I should also mention very informally that if two graphs G and H are close to each other, then some standard spectral properties of matrices imply that their spectrum is somewhat close to each other. So if you pick a Turan graph and slightly modify it, then lambda2 is going to be still small. So by slightly modifying, I mean you pick a small collection of edges and non-edges and change their status so that you still remain regular. That's a little bit tricky to formalize, but that's sort of good to keep in mind, at least on an intuitive level. Yeah.
What is this? Remark number 3, contradicting the statement of Alon and Boppana.
No, because for the complete bipartite graph, the diameter is
2 R's.
2. Yeah, maybe I have my constant off. The point is, I think this is true if I add in condition D is 3. But basically, you should only think of this Alon Boppana bound as let the diameter be larger than 3. The sort of examples when the diameter is 1 or 2 are a little bit silly because, and to some extent 3 as well, because it's not really thinking anything. It's more like when the capital D is either a large-ish constant or tends to infinity that we care about. I mean, when the capital D is small constant, the applications we really care about is that it grows proportionally to the square root of D. What we'll state now is that actually this 2 is the best possible constant. So in the regime when capital D tends to infinity, that's also interesting because then we sort of get the best possible bound in the sense that this constant 2 can be improved. But yeah, you should either be a capital D tending to infinity with n, or if it's constant, then you should only think of this bound as lambda2 being proportional to root D. Instead of the dense regime applications, what you really usually care is this one. Or what's the sort of well, the other bounds are slightly different, but you don't care about what the explicit constant in front of the function depending on D is, but rather what's the asymptotic growth rate of lambda 2. So Friedman proved that up to any additive constant, this bounded lambda 2 is the best possible for random graphs. When n tends to infinity. And finally, where is this 2 times d minus 1 kind of heuristically coming from? So let's now look at the case, let's say d equals 3. So for every d, we can construct an infinite d regular tree. So basically you start with a vertex, you add d neighbors to it, they have d neighbors, and so on. So let TD be this. So the notions of adjacency matrix or the adjacency maps make sense for infinite graphs as well. So basically, given a vector f, so label these vertices as v1, v2, and so on, and then you can define an adjacency. I don't want to call infinite matrix, but you can think of as a map where aij is 0 for, like for each I there are 3 j's for which aij is 1, and for others is 0. And then given a vector f with infinite many entries, so that the L2 norm of f is 1, it's really important, then we can define AF as this vector where the ith entry is just given by this sum, and note that this sum has 3 non-zero entries. So in Polygon, that's a very well-defined number for every vector f. In addition, it's not too hard to prove that this f is gonna AF is gonna have a bounded L2 norm, and then we can define AFF as usual. And again, it's not too hard to prove that if f has a bounded L2 norm, then this inner product is finite. So we can define the spectral radius of this operator A as the the supremum of the products of f and af among all the vectors f being L2 alone being 1. So if A were an adjacency matrix of a D-regular graph, then this would be just D, because we can take the O1 vector that corresponds to top eigenvalue. Here we can't take the O1 vector, because the O1 vector, you can't try to truncate it. So you start with having, one decent guess, I guess, could be you put 1 for these 4 vertices, scale it down, or you put 1 for everything which is distance 2 from the root, scale it down to have a unit vector, and so on. That's actually not doing too well either. So what happens is that you can show that this, what you get as spectral norm of A is 2 times root D minus 1. And basically the vector you're about to construct, we'll see soon when we prove the Alon Boppana theorem, and that basically motivates our proof bit. And one good candidate could be you fix a number here, you fix some numbers for the neighborhood, you fix a third number for the second neighborhood, and so on. That's not actually the best possible. Instead, you should rather fix an edge here, pick a same number for that, those 2 vertices. Now take the neighborhood of the edge. So these 4 vertices, fix the same number for those, and keep going. So it's not sort of super hard to guess that some sort of this type of construction where you fix a small gadget and then have a constant weight on that gadget, and then look at the neighborhoods, because this sort of, well, it comes naturally how this operator acts should be the best one. And then if you now have a D-regular graph, this infinite D-regular tree is something called universal cover of the graph, meaning you can find a surjective homomorphism from this tree to your favorite D-regular graph. I'll not go into full details what it means, but basically, if you there is a function so that if you look at the image of this vertex, then this vertex and its neighborhood maps bijectively to a vertex in your host graph and its neighborhood. So kind of locally, D-regular graphs sort of can be viewed as not quite subgraphs of this infinite D-regular tree, but for our purposes, sort of the lack of edges here that might be present in some neighborhoods of D-regular graphs doesn't hurt us, but actually Alon Boppana theorem is kind of the most difficult when your graph sort of intuitively has a large girth as well. So when locally it looks like a D-regular 3 like graph. Okay, that's a lot of informal chatter about the theorem, but I think it's sort of good to motivate a little bit where the proof is coming from, what are the connections to other things, and how you should interpret the theorem. And one thing I should also say is that, very briefly, there are also notions of adjacency tensors for hypergraphs, and you can consider similar spectral properties for them. And then you also have natural analogs of infinite D-regular trees, but there the correspondence breaks down. So there the corresponding sort of eigenvalues, so to speak, of the adjacency tensor would grow like d to the 1 over r, where r is the uniformity of the adjacent of the hypergraph. But actually, you can prove that for the second largest eigenvalue of any regular hypergraph grows at least root d. I think there are more important topics to cover towards the end of the week than the adjacency tensors of hypergraphs, but if you're interested, it's good to be aware of that. Recently, this problem has also been studied for hypergraphs as well. Good. So let's actually now prove the Boppana theorem. So let's fix a proof of an edge here. And I should mention that because so I want to just show the proof idea. So I'll implicitly assume that D is strictly greater than where R is, I don't know, let's say at least 2. So let's not worry about the cases when D is a very small constant, but rather look for the regime when D tends to infinity or capital D is a large constant. And then I want to prove something like this sort of a bound where here I have R. So maybe I'll be off by constant 1 over here, but that's sort of just to make sure that we don't have to worry about all the tedious details. The idea is still similar. So fix an edge in the graph.
Parameter R.
Sorry?
What is the parameter R?
To be chosen later. What I'm just saying is that if you think what I'm going to prove doesn't make sense when the capital D is 3, 4, or 5, then I'll say that's not important for the intuition. Let's assume that the capital D is sort of a decent sized constant or tends to infinity. So let Vi denote all the vertices in W in V, so that the distance from U or so the distance from either U or V is exactly I. So what it basically looks like is that here we have the edge. This is our set V0. The neighborhoods form a set V1. Maybe there is some edge across. So we don't add this vertex to V2 because it's, even though it's distance 2 away from U, it's still distance 1 away from V. Then they have a neighborhood. We call this V2, and so on. And we only define this for I between 0 and R. And we define a vector F such that its W's coordinate is 1 over D minus 1 to the I divided by 2 if W is in VI and 0 otherwise. Basically meaning that the numbers over here we assign weight 1, here we assign weight 1 over D minus 1, here we assign weight 1 over D minus 1, and so on. And then at some point we'll make a cutoff, and the rest will get weight 0. Instructively, in this example, we put the weight 1 over here. 1 over d minus 1 over there, and so on. So in this infinite tree example, we could keep going indefinitely. In our graph example, because we are just trying to find an approximate structure that looks like this, we are going to stop at some point. So at this point, our goal is to show that this is large. And let's just, as a second, recall that lambda 2 is the supreme over all w, which is non-zero, and w is orthogonal to the all-one vector of w, the inner product of w and aw, divided by the L2 norm vector. If you want to scale your vectors to have L2 norm 1, then it's just the supreme over the inner product of aw and w amongst those which are orthogonal to the all-one vector, namely the eigenvector. Okay, so our choice of f is certainly not going to be orthogonal to the all-one vector. So now it's a good question to ask, is it a problem? Turns out that it's not, because I only define these sets up to sort of the halfway of the diameter. So if I can prove that this inner product is large, then what it looks like is that I have some vertex in graph U and some vertex with W, which are distance 2 plus 2 apart. I draw this picture that covers roughly the R plus first neighborhood of my vertex U, because I have to pick an edge and draw this picture, and it has things which are distance R away from B, so at most R plus 1 away from U. And now I can sort of repeat this picture with W and construct another vector. And here, note that all the entries are positive. And the point is that when we take this inner product, the positive entries reinforce themselves. Now for this complementary structure, I could pick all the entries to be negative, and that's good because then they will again reinforce each other. And the point is that here the supports of f and this other candidate vector f prime are going to be different. And also, if we take the neighborhoods of their supports, there's going to be disjoint. So there's not going to be any interaction between them. So then I can just take the linear combination of these two vectors, and I can ensure that some of these linear combinations is going to be orthogonal to the all-one vector. And when I take the inner product of the linear combination together with A of the linear combination, then actually there is no interaction between those two terms. I'll write that down at the end, but basically, by this informal chatter, hopefully you're convinced that this sort of verifying that this is true basically morally solves this, prove this Alon Boppana
That
theorem.
one should be the inner product of W and 1 is 0.
Yes, thank you. Yeah. So we want it to be the orthogonal. So this is now the condition we are lacking, but by this informal chatter, that's sort of not too difficult to fix. And that's why sort of the case when the diameter is very small is a bit tedious, because here we might have some sort of a suboptimal rounding error with these constants. We want some room to play around, but it's also the regime which is not super interesting. So that's why, save myself from some technical details, I'll just assume that the capital D is somewhat large. Okay. Some lower bounds for AF of W when W belongs to AI. Okay, so by definition, this is just sum of FUs for U in the neighborhood of W. So if W is in AI, it means that all of its neighbors are at worst contained in AI plus 1, and it has a one neighbor in AI minus 1.
You mean VI?
Yes, sorry, yeah. Thank you. So, in particular, it's going to be at least d minus 1 to the minus I minus 1 over 2. This is because it has at least one neighbor in VI minus 1 plus d minus 1 times d minus 1 to the minus I plus 2 over 2. I kind of want the exponent to be actually clear, so let me write it again. And again, this is because the remaining
If W lives in AI, should that be in VI?
yeah. I think when I was writing the notes, I probably used AI. Sorry about that. Yeah, so anyway, so we have this one good neighbor, which gives us a lot of weight. And with the remaining ones, we don't really know what happens apart from at worst they are on the level below. So let's use that as a lower bound. Guided by our this infinite binary tree example, that's kind of like the best possible we could hope for. And especially if the girth of G is going to be large, that's what's going to happen. Because if we don't have small cycles, then basically you always are forced to go to the level below unless you are the unique neighbor that guarantees that you are in level BI. So that's just going to be 2 times the square root of d minus 1 divided by d minus 1 to the I over 2. But I'm cheating a little bit. I'm assuming that I is not in the last level. That there is this level below. Because if I belong to BR, you belong to BR, then we don't have the second term in the sum. And that's basically where the error term in the Boppana theorem is coming from. So on the bottom level, we only get this first term, but that's still fine. So in particular, if we take the inner product of F and AF, then okay, so on level I, there are BI many vertices. For each of them, f of u is going to be 1 over e minus 1 to the I divided by 2. And AFU is going to be this number. But then we have to subtract the sort of the error term we get from the last level, because there we only have we don't have the factor 2. It will be a lower one, right? Sorry, a lower one. Yes, thank you. So that's indeed a lower bound for the inner product. Yeah. But recall that our f is not quite a unit vector, so we also have to control what's the L2 norm of f, because we are interested in the ratio of these two. But that's quite easy to count. So it's going to be just and here I have b minus 1 I. So in particular, this term is just the L2 norm of f squared. And this just follows from the fact that each vertex in BI has weight square root of 1 over square root of d minus 1 to the I, and there are BI of them in here, or the number of BI of them in BI. Finally, we know that the size of BI plus 1 is at most d minus 1 times the size of BI. Why? Because everything in BI sends at least one edge to BI minus 1. And still they have d minus 1 other neighbors. And sort of in the worst case, all of them are in BI plus 1, which gives the upper bound for BI plus 1, if they all give generally distinct neighbors there. So in this way, an upper bound for BR in terms of the L2 norm of F. So we conclude that this ratio is at least 2 times square root of d minus 1 minus 2d minus 1 Boston constants. Again, I'm intentionally a bit sloppy here. That's not the main sort of part of the argument to figure out what these actual constants are. Basically, because if you iteratively use this bound, you can get each of these terms, I believe is at least the size of BR, and there are R plus 1 of them. at least VR divided by d minus 1 to the r. There are r plus 1 of them, so I think what you get in the here is actually just r plus 1. If I screw up something, it's easy to fix. That's not the point. The point is that the main term we get is 2 times root d minus 1, which is what we are intending for. Any questions so far? So recall that our choice of stage UV was arbitrary. So now let's pick U and W so that their distance is at least 2r plus 2. And pick the first edge to be UV and the second edge to be the UV1 and the second edge to be this WW2. Sorry, V2, let's say. And construct F and F prime for these edges and for this choice of R. Let's actually assume that we have a strict inequality. The support of F, i.e. the set of non-zero entries, is contained, or actually equal, well, yes, it's contained in the vertices which are at most distance r plus 1 away from U. And similarly, the support of F prime is contained in this set. So if we take the support of AF, it's contained in one more neighborhood of U. And this is disjoint from the support of F prime. So it's contained in the complement support of F prime as the distance between U and W is strictly greater than 2 plus 2. So in particle, we conclude that these inner products are 0 because we are considering pairs of vectors with disjoint supports. So basically, when we write this inner product as a sum, every pairwise product of the coordinate-wise entries contain at least one non-zero, one zero entry. So each of the n terms in the product, n products in the sum are going to be 0. So now let A be some linear combination of these vectors. Actually, we can just pick the coefficient for the vector to be 1. Now, the inner product of A and AA is going to be given as follows. But by our previous observation, these terms are 0. And that's crucial because in our construction, we want sort of, so both f and f prime have only positive entries. So we really want this beta to be negative so that we can get any hope for A to be orthogonal to the Alon vector. So then what's really going to drag this down are these cross terms. But because they are supported by different sets, we know that they are 0, so they don't hurt us. But by our observations, these inner products are at least 2 times d minus 1 minus the error term, so plus constant, some constant c divided by r plus 1 times the inner product of f with itself plus beta squared times f prime itself. But this is just a L2 norm of A squared, because f and f prime are also supported by these different sets. So now we just choose A so that A is orthogonal to the Alon vector to conclude that lambda 2 is at least as large as we wanted. Good. Yes.
When constructing such a vector like f,
Yep.
I believe a natural state would be just start from a vertex and consider its neighborhood.
Exactly.
But instead,
With
we
bigger
choose
f.
an edge.
Yes. That's a good question. That's indeed a natural construction to try. That gives you a bound of the form constant times root d for some constant less than 2. The reason why we choose an edge is that basically if we now look at the case when f is like this proof, what is f times af? It's going to be sum over u and v, so that u is a neighbor of v of fu fv. In the example you gave, basically what the terms we're going to have is that u belongs to some level I, v belongs to some level I plus 1. And we have similar sort of decay by factor root d. And that's going to be a problem because we have sort of a bit too large decay. One reason why we get a gain from considering the edge is that we have 2 of these large entries, 1 and 1, which reinforce themselves. Because here, when we do it with an edge, one of these terms is going to be 1 times 1, which is missing from this sort of a so-called Hamming ball around the vertex construction, because they're sort of, we never have a large term times large term because we always have a terms on different levels. So that's why picking an edge is a good thing, because there we sort of start first by multiplying 2 sort of a large things together because there's edge between them, and then we decay. That's why you sort of it's a natural candidate to try, but it's unfortunately not going to work. And that's why sort of this infinite deregular tree is a good example of try, because there you sort of know is that you have this worst case scenario where you don't have any cycles. So there you can basically treat this as an optimization problem. You assign a variable to each thing, then you are basically optimizing this infinite sum over a bounded L2 norm, you can try some tools like, well, I haven't done it ever, but I probably imagine some sort of a Lagrange multipliers or so on can give you some sort of proof where the extreme is achieved. If you actually phrase this Alon Boppana theorem by using Laplacian matrices, which is a slight formation of adjacency matrix, then it becomes another type of optimization problem where some people claim that it's easier to see why this example is why this choice of vector f is the optimal. I sort of slightly disagree, but I guess it's one of the things where you just have to sort of treat it as an optimization problem, try a bunch of candidates, and then once you find the best amongst the natural ones, don't just stick with one, find the best among the natural ones, and then try to sort of see from the proof whether it's actually good. And in this case, Friedman proved it is also the type of. And also this sort of infinite deregulatory example sort of gives some confidence why this should also be sort of not improvable. Okay, let's have a quick 5-ish minutes break and then continue. Do the better one, you prime their neighbors, B, W prime, and put a constant weight. But basically the idea is that you sort of find a small gadget, here it's the edge, you look at their neighbors, the sticky neighbors and so on, and have a constant weight on each of those cells. And then you have the similar sort of a structure at the sort of other extreme end of the graph, namely a vertex which is far away in terms of distance, and you do the same there. Then you sort of scale them properly, so that it's going to be orthogonal to all one vector. And the point is, why is this a good thing to do? It's basically when you look at the inner product of f and AF, then the large terms sort of reinforce themselves because you have a lot of terms of the form fi times f, fu times fv for u and v being on a sort of adjacent layers, bi and bi plus 1. And why do you pick an edge rather than a vertex? It's because you want to sort of get started with a large term. You want, because the sort of 1 times 1 term is going to be quite large in some already. Okay, so now we're going to move to a completely different topic.
So people care about, that way, do people care about, say, nearly regular graph? Because I feel like for exact regular graphs, this is usually 2 regions on the restriction side. For example, like every degree d is in some d plus minus epsilon, then.
So if your graph is nearly regular in the sense that the top eigenvector is close in L2, sorry, the difference between the top eigenvector and its projection to the Ullmann vector, sorry, the top eigenvector has a large projection to this space spanned by the Ullmann vector. If you define that as a notion of being nearly regular, then a lot of the proofs generalize to near regular graphs. It's a bit hard to intuitively describe what that means in terms of the degree sequence, for example. But yeah, you are right that often we care about notions of where the graph is not necessarily regular, but actually that's like that. And the study of lambda 2 in the somewhat dense regime actually has applications in the study of equiangular lines. So Igor Bala used it recently to get some as a tool, like basically why there has been a study of lambda 2 in the regime and d is greater than 1/3 came from the fact that it was actually needed for another problem, or one of the reasons. And in those applications, as far as I remember, some of the sort of, in some of the results I got about like far away from being regular. But obviously, the tools he used also give bounds for lambda 2 when the graph is irregular. But those are sort of I'll show some results which are motivated by them, but it's sort of a bit too technical to discuss in great detail. No. Okay, so discrepancy should be viewed as a notion analogous to the max-cut problem. So given a subset of the vertices, we define the discrepancy of the set U to be the number of edges inside U minus P at edge density times the size of U choose 2. Okay, so if we now pick a subset from the vertices of G uniformly at random of size of the same size as U, then by linearity of expectation, this is exactly the number of edges we would expect there to be. So basically, the discrepancy of U is just how much E of U deviates from its expectation. So we define the discrepancy of G to be the maximum deviation you can achieve, whether or not it's positive or negative. So we measure it in terms of the absolute value. The positive discrepancy to be how much this deviation can exceed the expectation, and the negative discrepancy to be sort of how far below the expectation can it be. So obviously the discrepancy is just the maximum of the positive and negative discrepancy. So the study of discrepancy dates back to Edwards and Spencer. Who proved in 71 that discrepancy of G is at least n to the 3 halves when P is equals half, and this is tight for random graphs. And then roughly a decade and a half later, Eros, Goldbach, Bach, and Spencer extended it to a wider range of parameters. And again, this is tight for random graphs, and this regime is optimal. So this implies that one of the positive discrepancy and the negative discrepancy is large, but it still leaves the question, how large must the smaller one be? So for random graphs, it's actually the case that not only one of these is achieves this bound asymptotically. Like here, by tight I mean up to multiple constants, but actually both positive and negative discrepancy are proportional to this number up to multiple constants with high probability. So it's not just that the larger one of them grows at least as fast as this function, but both of them. So, however, the positive and negative discrepancy can be substantially smaller than these bounds. So recall that we write TRN for the run, so the R-partite run graph on n vertices. Then it's not too hard to verify that the positive discrepancy of these guys grow linearly in n, and the negative discrepancy of their complements also grows linearly n. So there is a clear symmetry between positive and negative discrepancy when they in complements. So the negative discrepancy of G complement is just the positive discrepancy of G just by plugging in sort of complementary relation in these formulas. So in fact, when P is in this range, so we saw this range yesterday. Remember that P being roughly greater than 1 over n means that the average degree is at least here we could replace this by a constant over n as well. So here the average degree is constant. So basically we don't see isolated vertices, or at least we like, okay, if we replace this by c over n and we take a regular graph or graph where the min degree and max degree are bounded, upper and lower bounded by a constant times the average degree, then we solving a regime where we don't see many or isolated vertices and so on. So we are not in a sort of a trivial regime. Then it can be proved that both the positive and negative discrepancies indeed grow at least linearly in M. And one way to prove it is to basically just do it greedily. It's a bit sort of a tedious thing to do, but removing vertices of max and or min degree sort of gives you these bounds. And by the examples of Turan graphs and their complements, so you know that complement of the Turan graph is just a disjoint union of equal sized cliques. We can't really get better, improve this greedy algorithm in general. However, in both of these examples, so for Turan graphs, the negative discrepancy is huge because they have linear as independent sets. So the negative discrepancy is proportional to n squared. And here, while the negative discrepancy is linear, the positive discrepancy is huge because we have linear as cliques. So picking one of those sets gives us positive discrepancy being n squared. So there, like in these examples, while one of the one-sided discrepancies is really small, much smaller than the n to the 3 halves we have in general, the other exceeds it by a lot. So it's nowhere near tight for this bound. And actually, that holds in general. available version and Scott put in 2006 and P in this regime, then there's inverse relation between the positive and negative discrepancy. In a way that their product is large. So, first of all, this is tight for random graphs. Also for two-run graphs, because here the positive discrepancy is linear and then negative discrepancy is quadratic and P is roughly constant. So this part is kind of the parameter that is proportional constant times n to n3. And obviously the complements. But also in many other examples, including all strongly regular graphs. We'll see that later when we prove some relations between spectral lambda 2, lambda n, and positive and negative discrepancy. Yes.
Then why the discrepancy for Trump graph is n?
Yeah, sure. So that's a good question. So let's suppose that we fix the size of u to be alpha times n. By a little bit hand wavy argument, but basically now suppose the set of size u being alpha n means that we choose a fraction alpha I n from each of these blobs in the two-run graph. A bit sort of a tedious optimization problem shows that actually it's the best to choose the same fraction from each one of them. And actually it holds up to the precision where if I actually give that this sign is t, not just a fraction of alpha, then each of these is going to be t prime or t prime minus plus 1, where t prime is the floor of n over r. So basically there are only two choices that can be taken. And now the number of edges in U is, so let's assume that we are in a case when all of these are equal. So what we get is there are r of them. So the edges inside U is r times, so it's r choose 2 times t prime squared. And size of U is r times t prime. So the edge is inside of U minus p times U choose 2 is another point is that here sort of the linear this positive discrepancy comes from the rounding error in the edge density. That if you look at the two-run graphs, the asymptotic edge density is 1 minus 1 over r. But if you look at the edge density of the two-run graph on n vertices, it's going to be 1 minus 1 over r plus something which is constant over n, which in general doesn't matter, but in these calculations it actually matters. because we then weight it against the size of you choose 2, and that's where the linear bit comes from. Do you want me to actually write down the missing calculations, or is this enough?
Yeah. So
Let's say that because I'm running a lot of time, I'll finish what I'm doing here, and then we can, I guess, stay after the sort of lecture finishes to go through the calculations if needed. So it's tight for a bunch of examples. It gives strong stability for the theorem of Eero, Goldberg, Bach, and Spencer, because it proves that the discrepancy is at least the square root of this number, which is exactly what they state is, and it proves that if the discrepancy is this number, then it follows that both are proportional to it. So it basically, what it means is that if we are close to the up to constant factor, to the smallest possible discrepancy we have, then it's not just true that one of the positive and negative discrepancies is large, it's actually true that both of them are large. So it's not possible to have an instance where one of them is, say, linear in n, and other matches this lower bound we have. But rather, if we are close to matching this lower bound, then actually both positive and negative discrepancies are large. And then finally, let me not write it down. It's quite easy to see that the positive and negative discrepancies are upper bounded by p times 1 minus p times n squared. Basically because, okay, let's assume that our density is almost half. We want to prove that it's bounded above by p times n squared. Then the number of edges, the number of edges inside U is at most p times n squared. This is an upper bound for positive discrepancy. And the lower bound as well, if U is independent, then it's at least minus p times n squared as well from the error term. So basically, when we divide this by p times 1 minus p times n squared, we get n as a lower bound. So n is a lower bound for the smallest quantities.
Well, I missed what you just said. So if G has discrepancy of order this.
Yeah. So if G is tight for this lower bound, so remember that. So okay, so it's also a consequence of this Bolova-Scott inverse theorem. So the largest one of positive and negative discrepancy is always at least p times 1 minus p times n squared, or the square root one. Now suppose that the larger one of the positive and negative discrepancy is constant times this number. Then by this inverse relation, the smaller one is also at least constant times this number. So actually, we get sort of a stability in the sense that if we are close to this lower bound, it can't never be the case that the larger one is proportional to this number and the smaller one is substantially smaller than it. But it has to be the case that both positive and negative discrepancy are close to matching this bound. So you could sort of think of this as the sort of like if one of them undershoots this bound achieved by a random graph, then the larger one must overshoot by same multiplicative amount. Yes, the constant factors don't really match up nicely, but all we care about is the growth rate anyway. So in that sense, it's true.
This is type for strong irregular graph. That means this is type for graphs of all density. There are examples. Oh no. I guess my question is it possible for certain density you can improve this product?
Well, it's also tied for TNP. Assuming.
All right. That's already.
Assuming P is not very small or very large. But am I allowed to spend 5 more minutes even though I'm running out of time?
Sure, yeah.
Okay, so there are 2 things I want to say. One is these notions are very closely connected to the Maxwell problem under some assumptions, and the bisection width problem, which is kind of like the mean cut analog. And the second one is how sort of, while we achieved that both of them can be at least linear, we haven't finished the question yet, really, because, well, Hong correctly, he asked the correct question in the sense that is this tight for all densities? And the product theorem is tight because of G and P. The minimum of positive and negative discrepancies is, however, another question, because Turan graphs and disjoint union of equal size cliques don't exist for all densities. So let me first address the second point. So, while the positive discrepancy of Turan graphs they only exist for densities 1 minus 1 over R. So what happens, say, when P is, I don't know, 1/4, which is not among these densities? Turns out the answer is very different. For P equals 1/4, we get, we can prove something like the positive discrepancies n to the 1 plus delta for delta actually greater than 0. Actually, well, as we'll see, all of these problems that I have discussed so far are very closely related. So this breakthrough by Shang last year basically says that, very roughly speaking, if the positive discrepancy of G is close to being linear, then G is close to being a Thorne group. So a very sort of strong stability is true for graphs with linear positive discrepancy. Also, similarity between these notions. So let's assume that once it follows that both the positive and the negative discrepancies are at least linear. So in this regime, I leave this exercise to prove that, let me just make sure that I get this right. Yeah. If the negative discrepancy is lower bounded by the surplus. However, the converse is unfortunately true, but the converse is true if G is regular. And yes, you could prove some sort of a stability in a sense that if G is not too far away from being regular, then the converse is also true. So for regular graphs, the notion of negative discrepancy and the surplus are pretty much the same. In some sense, this means that the negative discrepancy is much more strict notion. So I guess sort of like here I have to spoil a little bit why the second one is false, but it's to give some motivation why we really care about the negative discrepancy. Really, this is false because we can add isolated vertices. So we can take the clique example and add isolated vertices. But that's kind of like in the max cut problem, we sort of already deemed that as a morally sort of a not really good reason why the max cut problem is sort of easy for given M for arbitrary n. So this is why discrepancy is sort of a little bit more, negative discrepancy is a little bit more natural thing to consider, because that sort of excludes this trivial obstacle, because in discrepancy we sort of care about both the number of edge vertices and the average degree. And here the clique case kind of automatically corresponds to the edge density being incredibly close to 1. So if we move away from it, then we are sort of guaranteed to be away from the regime when the discrepancy is small. Because for the example of clique and lots of isolated vertices, the negative discrepancy is quite large, because we can just take the set of isolated vertices as our U, and that has a very sort of a small discrepancy. Finally, we can define the bisection width denoted by BW of G to be the maximum of the partition of the vertices, and now with A and B being very close to each other, of M divided by 2 minus the number of edges. So this is kind of like the min cut, the smallest size of a cut, but obviously other sort of excess in the depth. Sorry, this rather the so the mean cut, the bisection width is just the smallest size of cut, and the deficit is this. So obviously we can't define bisection width to be the minimum number of edges between A and B for all the cuts, because we would just take A to be the empty set and B to be all the vertices. But a sensible notion to define it is amongst all the cuts which split our vertex set into equal size. Then we sort of fix this trivial obstacle preventing us to define the natural sort of analog of the max cut. And then we just say the deficit is how much it differs from the average. And similarly, we can prove analogous statements between positive discrepancy and deficit of G. So these two notions are also closely related. So tomorrow we are gonna prove the Boppana theorem. That also, the same technique can also be used to prove this lower bound, which is highly non-trivial. Because think of this as, now we have established, sorry, I'll keep going for 2 more minutes. So now that we have established this correspondence between the max cut and the surplus, we see that this corresponds to the surplus being m to the 3/4 for random graphs, which is more than what we have for cliques. So the techniques used in the proof of Boppana theorem kind of like reveals how random graphs behave to all of these questions. Then we're going to also discuss the relation of lambda2 and lambda n for this positive and negative discrepancies, and then that problem, and also how can we prove lower bounds for positive discrepancy, which substantially beats the because the discrepancy problem for graphs of average degree makes much more sense than the max cut problem, because once we specify the edge density for these one-sided discrepancies, we can't use the clique example anymore. And that also gives us Alon Boppana type of theorems for other regimes of D. Good.
In exercise number 1, what does SPG mean?
It's a surplus of G, defined yesterday. So it's how much the max cut exceeds the M over 2.